In this video, we're going to be looking at topic 8b, which are the elements of group 1 and 2 of the periodic table, and this is part of the IAS chemistry course from Edexcel, and this is in unit 2. So we're going to be looking at different trends within group 1 and 2, so we'll be discussing ionization energy, reactivity, and we'll also be looking at the reactions of the elements as well as the reactions of their hydroxides and oxides and their trend in solubility. We'll also link into thermal stability as well as flame colours and how we carry out a flame test and why flame test occurs, as well as the reactions for identifying carbonate ions, sulfate ions and ammonium ions. So let's start off by looking at groups 1 and 2. So there are 6 elements in each of groups 1 and 2. Group 1 typically known as the alkali metals, and group 2 known as the earth alkali metals. So group 1 is lithium, sodium, potassium, rubidium, cesium and francium, and group 2 is beryllium, magnesium, calcium, strontium, barium and radium. With the exception of francium and radium, all of these are pure silver solids when they're not exposed to air. Now we know that they are going to tarnish when they're exposed to air, and we will look at that reaction later on. And for each of these groups, we should know the trends in ionization energy and in reactivity. So just a reminder, ionization energy is the energy required to remove 1 mole of electrons from 1 mole of a metal when it is in the gaseous state. So you would get something that looks like this equation. And you learned this back in topic 2. So as we go down groups 1 and 2, the ionization energy decreases. And this is due to the fact that the energy needed to overcome the electrostatic attraction between that outer electron and the nucleus is much lower. And this is because the atom is getting larger. So we're seeing increased shielding. Or you can say it as increased electron-electron repulsion. So as the metal gets larger, as you go down the group, you can see the metallic radius going from 0.152 up to 0.262. That means the outer electron is much further away, therefore it requires less energy to be removed as it's not attracted to the nucleus as much. So we see a decrease. When we're looking at group 2, of course, we can have 2 ionization energies because we can remove the first outer electron and then the second outer electron. We're not going to go into any further ionization energies of 3 or 4 for these elements. If you want to have a look back at how we write those, have a look at your textbook or your notes from topic 2. So the main factors that we have to consider when we're explaining the trends are the nuclear charge of the atom, the orbital in which the electron exists, and the shielding or repulsion effects. So let's look at each of these individually. So the nuclear charge of the atom should increase the ionization energy because we are getting more protons. So we should see there being more of an attraction, and this should give us an increase. However, the orbital in which the electron exists is going to be higher at a higher energy, therefore the energy required to remove it tends to be less. So this addition of the quantum shells and increasing the energy is going to cause a decrease in the ionization energy. And the shielding and repulsion effects from the inner electrons, again, that repulsive force is going to increase because we're going to get more and more of electrons, so more and more repulsion, and that will cause a decrease in the ionization energy. So the combined effect of the second and third factors vastly outweighs the effect of the first, giving us an overall decrease. So when you're explaining the trends in ionization energy, you can mention that there is an increase in nuclear charge, but that is not what actually controls it. What controls it is the fact that the outer electron is in a high energy orbital, and we're getting increased shielding as well. So when we're looking at chemical reactions of group 1 and group 2, we can see that the element is going to change either into an M1+ or an M2+ ion, and M just stands for any metal in group 1 or group 2. And the trend that we see going down groups 1 and group 2 is that the reactivity increases. And this is linked to the ionisation energy. The less energy it requires to remove that outer electron, the more likely it is to happen. Therefore, as you go down the group and that decrease in energy is seen, it means that it is more likely to form an ion. So we get a decrease in energy to remove the outer electron. So ions are more likely to form. Therefore, these chemical reactions that we see are more likely to happen. So let's start off with the reactions of group 1. Group 1 metals are going to tarnish when they are exposed to air, and this forms a dull, dark layer on the surface. And this dull, dark layer is our metal oxide. And this is because they're being oxidized by the oxygen that is in the air. Even though there's only a small amount of oxygen in the air, remember there's 21%, it is still enough to very rapidly react with the metal to give you that dull metal oxide. They can also react with oxygen in combustion reactions if we add in heat. And the general equation for this is 4 atoms of our metal M reacting with an oxygen molecule to give us 2 molecules of M2O(S). Group 1 metals can also react with chlorine gas when they're heated, and that gives us the general reaction of 2M plus Cl2 giving us 2MCl. Remember here, both of them have a valency of 1, so they are going to be in a 1-to-1 ratio, as opposed to here, where they are going to be in a 2-to-1 ratio with the metal to the oxygen. Group 1 metals are also going to react very violently with water, and they get more and more vigorous as you go down the group. When you get to the bottom of the group, the reactions actually become explosive. The key ones that you have to know are lithium, sodium, and potassium. You can then make predictions about the others based on the trend that we see. So when lithium is added, we see fizzing due to the production of hydrogen, and it floats on the surface. When we have sodium, again, we have fizzing due to the production of hydrogen, and we see the sodium melt into a ball. That's because the hydrogen that is being produced is just short of actually igniting, but it is giving a very, very high temperature because this is an exothermic reaction, and it causes the sodium to melt, and again, it floats and moves on the surface. Potassium is slightly different, that when we add potassium, the hydrogen actually ignites and we see a lilac flame being formed. You'll have seen these reactions back in IGCSE, and if you haven't actually seen them in real life, you can find videos on YouTube if you just search alkali metals in water. And the general reaction that we have here is 2 atoms of the metal reacting with 2 molecules of the water to give you 2 metal hydroxides and hydrogen gas. So now let's move to the reactions of group 2. These are very similar reactions. What you'll notice is that simply most of the time it is just how vigorous they are, or the formula of the substance that is being formed that changes. So our group 2 metals can also tarnish when they are exposed to air, giving that dull, dark layer of a metal oxide. What you will see is that this tends to be slower than group 1, but it does still happen quite quickly. They can also undergo combustion reactions. This time, however, we have a slightly different general reaction. We have 2 metal atoms reacting with the oxygen molecule to give us 2MO, with our metal and our oxygen being in a 1-to-1 ratio. The group 2 metals can also react with chlorine, again giving us 1 metal atom reacting with the chlorine to give us MCl2, a ratio of 1-to-2 between the metal and the chlorine. Now, when we're looking at the reactions of group 2 atoms with water, what we see is that the reaction with magnesium is very, very slow, and it actually doesn't go to completion. So magnesium does not react particularly well with water, and that again fits in with our trend that group 2 tend to be less vigorous than group 1. However, calcium, strontium and barium, as we went down group 2, are all going to react, and we are going to see that increase in the reactivity, and we see an increase in effervescence. Notice at this time we see no flames. The flames, such as the lilac flame for potassium, will only happen with group 1 because they are reacting so quickly. And you can see that we have our general reaction. The main thing that is changed is now our metal and our hydroxide are now in a 1:2 ratio because of the charges. Now, magnesium can still undergo a reaction with water, it just needs to be in the form of steam. So we need to have it heated and in the gas phase. So it won't react with liquid water, but when we react it with steam, it very rapidly will form magnesium oxide and hydrogen gas. And you can see that in this equation here. And what happens is the hydrogen gas is burned at the end of the tube, and that's just to avoid that highly flammable gas from going into the lab. You may also carry this out in a fume cupboard, but we just make sure that any hydrogen that's being produced is always burned off to remove it, and we are left with our magnesium oxide product. So now let's move on to the oxides and the hydroxides. So group 1 and group 2 oxides are what we call basic oxides. And that means that if they react with water, they're going to form colourless solutions of alkali. So relating that to pH, we're going to have a pH of all of these of above 7. And if we react group 1 or group 2 oxides with water, you can see the general equations here, we're going to form these metal hydroxides. Okay, and we can actually simplify these by removing the spectator ions and have just the ionic equation where we have our oxide ion reacting with the water to form 2 hydroxides, because you can see that we have no change in our oxidation number or the charge on our ion. It still is 1 plus for group 1 and 2 plus for group 2. Now the hydroxides that we form will have again a pH above 7 because they are of course alkalis, and the pH of the alkali will depend on the solubility of the metal hydroxide. Okay, and what we see for the trend is that the solubility is going to increase down the group. And that means that the maximum alkalinity or your pH value is going to increase. So as you go down groups 1 and 2, you're going to see much stronger alkalis being formed as you would at the top. So for example, magnesium hydroxide is insoluble, so we're not actually going to make an alkali, but barium hydroxide is soluble, so we will make an alkali, and that has got a fairly high pH. We see a similar sort of trend for group 1, where we've got sodium and potassium giving you varying degrees of alkalinity because we see this solubility trend. So our solubility is going to increase down the group. You have to know the trends. That is the most important part. So if we look at calcium hydroxide, so in group 2, we have CaOH2, and when we react it with water, we can form our calcium carbonate precipitate. And we can use this as the chemical test for carbon dioxide. So you'll have seen this back in IGCSE. You'll see a picture like this where you have what you would call lime water, which is just another word for calcium hydroxide, and it's going to form this milky or cloudy suspension, and that is because we are making this white precipitate of calcium carbonate. We can also use calcium hydroxide to neutralise soil in agriculture. So you may sometimes hear of people spreading lime on their fields. That is not, of course, the fruit. That is calcium hydroxide that they are referring to. Magnesium hydroxide, on the other hand, is not particularly soluble. In fact, it's almost insoluble, but it can form something called a suspension. So that's when we have the magnesium hydroxide being suspended in a liquid, typically water. And we call this milk of magnesia. And actually, this is sold as an indigestion remedy, because we have hydrochloric acid in our stomach that can sometimes become too acidic and give us pain or heartburn. And if we take milk of magnesia, that is obviously going to have some alkali or basic properties. So it's going to undergo a neutralization reaction, and it is going to neutralize that hydrochloric acid and relieve the symptoms. Now, all of our group 1 and 2 oxides and hydroxides can react with acids to form salts and water, and these are our neutralization reactions. And we've come across multiple examples of these all the way through GCSE and to A level. The only observation that we see is a white solid, because they will all be in solid form, reacting to form some sort of colourless liquid. Okay, so we can't actually necessarily see the salt being formed, we just simply see a colourless liquid, which will be our salt dissolved into the water. But we do see a temperature change, as these are exothermic reactions. And we've got some examples down here. So probably one that you're quite familiar with would be your potassium hydroxide reacting with your hydrochloric acid to make potassium chloride and water. That's a typical example that you may actually even have carried out in the lab. But we can also have our sodium oxide, calcium oxide, and barium hydroxide all reacting with varying acids to form a salt and water. Now, when we look at the sulfates, and particularly in group 2, we see a slightly different pattern in terms of their solubility. Now, for group 2, nitrates and chlorides, they are all going to be soluble, and you'll have learned that back in topic 2G, which was salt preparation in IGCSE. But when we're looking at the sulfates, what we actually see is their solubility decreases as we go down the group. So magnesium sulfate is soluble, calcium sulfate is slightly soluble, but strontium and barium sulfate are insoluble. And the low solubility of this barium sulfate is one of the main reasons why we use it as the chemical test for sulfate ions. So you'll have seen that if we have a suspected sulfate compound, what you'll most likely do is add barium chloride to it, and then you will see that you get a precipitate or a white precipitate being formed, and that is generally your barium sulfate, and that tells you that the sulfate is present, so your chemical test is positive. Sometimes you may also hear of the barium being used in something called a barium meal, and that's taken by patients in hospitals when doctors want soft tissues to show up on x-rays. Typically, x-rays can only be used to look at bone, but if a patient has a barium meal, they get a buildup of this barium sulfate in their stomach or in their body, and it then shows up on x-rays, and that can allow soft tissue damage to be identified. Now let's look at the thermal stability of our group 1 and group 2. This is a very common exam question, typically 3 or 4 marks, and you have to know not only how it happens or why it happens, but also what the trends are in group 1 and group 2. And we're looking specifically at the nitrates and the carbonates. So what is thermal stability? Well, it is a measure of how stable a compound is when it is heated. If a compound does not decompose when it is heated, then we class it as thermally stable. Now, please note that there is a difference between decomposing and melting. Melting means just simply a change in state. Okay, so going from solid zinc chloride to molten zinc chloride. That would be a change in state. If it decomposes, that means a chemical breakdown. So that means that your compound is going to undergo a chemical reaction and break down into new compounds. So there is a difference between these two. They are not the same thing. And if a compound does decompose when it is heated, then it is classed as not thermally stable. So let's just make sure that we use the correct terminology and we're talking about thermal stability and not about melting. Now, our large complex ions such as nitrates, which is NO3 minus, or carbonates, which is CO3 2 minus, these are much larger than some of the other anions that you'll meet, such as chloride or bromide. These are more likely to decompose on heating rather than melt when you compare them to these smaller, less complex ions, such as the halides. So that's why we're going to focus on the thermal stability of just the nitrates and the carbonates. And there are differences between the nitrates and the carbonates in terms of group 1 or group 2, and it is all to do with different physical properties of the group 1 and group 2. Group 2 cations are going to have double the charge of a group 1. So calcium is going to be 2+, whereas sodium is going to be 1+. You tend to find as well that group 2 cations are smaller than that of group 1 in the same period. So that just means that the electrons in group 2 cations are held more tightly to the nucleus as opposed to group 1, making the ionic radius smaller. If we compare our chloride anion to our nitrate and our carbonate, we're looking more at the complexity and also the size. So these are going to be much larger than your just simple chloride ion. Nitrates and carbonates are both made up of at least 4 atoms, all with their own individual electron shells, giving you an overall compound, whereas chloride anions are just one simple anion. So if we have a nitrate ion, or NO3 minus, it can decompose into a stable nitrite, which is NO2, or it can be decomposed into an oxide, which is O2 minus, and depending on which one it goes to, we will release oxygen and or nitrogen dioxide gas. And we'll look at an example in just a minute. Carbonate anions will always decompose to the same thing. They will always decompose to an oxide, which is O2 minus, and they do this by releasing carbon dioxide gas. Now, the stabilities of your nitrate and your carbonate ions are influenced by the charge and the size of the cation that is present. A typical exam question will ask you to compare two nitrates or two carbonates, potentially with a group 1 and a group 2 cation, and ask you to compare as to why one decomposes and one does not. And these are the points that you have to make. So a smaller, highly charged cation is going to affect the anion more, and it is all to do with polarization. So you talked about polarization back in topic 3 when you were looking at how a cation affects the shape of an anion, and it does it by distorting the electron density. And this distortion is known as polarization. When the anion is polarized, this weakens the bonds and it allows them to break down much more easily. So we want a small charged cation because that is going to give us more polarization, which is going to weaken the bonds of the anion, which allows it to break down more easily. Now, in an exam question, this would typically be 3 or 4 marks, and these are the points that you have to make. And we'll look at an example of this later on in this video. So if we compare the ionic radii of group 1 and group 2, what you can see is that the ionic radii of group 2 elements is smaller than that of group 1. So not only do they have this higher charge, they also have this smaller radius, meaning they are going to have more polarizing power. And as we've explained, this is going to cause them to polarize the anion to a greater extent, causing the electron density to become distorted. This weakens the bonds within the anion, and therefore they are more likely to break down into different compounds such as oxides or oxygen or nitrites, depending on whether it is a carbonate or a nitrate. Now, if we look at the thermostability of the nitrates, our group 1 and group 2 nitrate compounds are white solids, and they're going to decompose to a nitrite 3 or an oxide 2 ion. And they're going to either give off nitrogen dioxide, which we see as brown fumes, and or oxygen in the form of steam. If we see no brown fumes, then we're getting a lesser decomposition, and that's making the nitrite, as we can see here. So we get the metal nitrate giving us metal nitrite and oxygen. So we don't see any brown fumes. If we have a greater extent of decomposition, we are going to see the brown fumes, because this time here we're going to make the metal oxide, oxygen and nitrogen dioxide. So what we see is that all group 2 nitrates are going to form brown fumes. This means that the group 2 have a greater level of decomposition. And that is because they are small cations with a high charge. When we look at group 1, what we see is that they can all decompose. However, from sodium down on the periodic table, we see a lesser decomposition. So from sodium down to cesium, these ones are going to form the metal nitrite as opposed to the metal oxide, whereas lithium is going to make the metal oxide. And we see the formation of oxygen and nitrogen dioxide as well. So we see these brown fumes, and that is because it's not to do with the charge this time, because they are all, of course, charged the same, but it is because the lithium has such a small size. So the greater decomposition occurs when the cation has a 2 plus charge, or if it's a 1 plus, the cation is very small. And you can see some examples here. So if you've got lithium, we're going to see this reaction. So 4 lithium nitrates decomposing to give you 2 lithium oxides plus 4 moles of nitrogen dioxide and 1 mole of oxygen. All of the other group 1 nitrates are going to have this lesser decomposition, which gives you the metal nitrite. So we have sodium nitrate forming sodium nitrite and oxygen. All of our group 2 are going to have this greater decomposition similar to lithium. The only difference is that your balancing is going to change slightly here, just because we have slightly different valencies in our formulas. So we have 2 moles of beryllium nitrate decomposing to 2 moles of beryllium oxide, 4 moles of nitrogen dioxide and oxygen. So now let's look at the thermostability of the carbonates. If you have a group 1 or group 2 carbonate, they are going to be white solids, very much the same as the nitrates, and when they are heated, there are 2 paths that it can go. It can either not decompose whatsoever, or it will decompose into an oxide 2 ion. If they do decompose, they are going to do so by giving off carbon dioxide, but we cannot actually see any observations this time, as opposed to with the nitrates, because our oxide is a white solid and our carbon dioxide is colourless. If we wanted to confirm that decomposition has occurred, we would collect the gas and we would test using lime water. And of course, if it was carbon dioxide, we would see the lime water going cloudy. So the equation for this reaction is the metal carbonate giving us a metal oxide plus carbon dioxide. And what we see is that the trend for the carbonates is the same as the trend for the nitrates. So all of our group 2 carbonates are going to decompose, and that is because they are small, highly charged cations, as opposed to the group 1 carbonates, where it is only lithium carbonate that decomposes, and that is because it is a small cation. The others are too large and too less charged in order to give us the level of polarization that we need to break down these bonds. So if we have lithium carbonate, they're going to decompose into lithium oxide and carbon dioxide. You can decompose the group 1 carbonates at extremely high temperatures, but this isn't particularly economical because it would cost too much money. So we don't even bother to do that. We want to try and keep any costs down if we were doing this on an industrial scale. And all of our group 2 carbonates are going to decompose in the same way. And the example we have here is calcium carbonate decomposing into calcium oxide and carbon dioxide. And remember, our greater decomposition occurs when the cation has our 2 plus charge, or it is a very small 1 plus. So the last section of this topic is to do with chemical tests, and you will have covered this back in IGCSE, but you just have to go into slightly more detail. The flame tests are chemical tests that are used to identify cations that are present in an ionic compound. And the method that we use is we dip a clean platinum or nichrome wire into concentrated hydrochloric acid, emphasis on the clean and the platinum. We then dip the wire into the ionic solid that is to be tested, and then we place the wire into a roaring blue Bunsen flame to observe the colour. You can also call this a non-luminous flame. That would also be accepted, and we see the colour. This method is a very common question in Unit 3, Practical Skills in Chemistry. So make sure if you are practicing those past paper questions that you do know how to carry out the flame test. So while flame tests can be very useful, there are 2 major issues that come with this. The majority of our ionic compounds that we're going to test are going to actually contain some sodium impurities. And sodium impurities are going to burn with a very intense orange colour. And what that can sometimes do is it can obscure or mask the actual flame colour that we want to see. So sometimes we get a false positive, or we can't identify what cation it is because the sodium is too intense. As well as this, describing colours is a very subjective process. People see colours differently, and they may be able to they may struggle to differentiate between the subtle differences or the shades in colour. What I see as blue-green, you may see as blue, or you may see as green, and that can have an effect on which cation you see is present. So there is that subjectivity here. Now, compared to IGCSE, where you only had to learn 5, now you have to know a lot more of the metal cations in terms of their flame colours. So you can see that we've got a table here that is taken from the textbook, and there is also some expanded colours in this diagram here. Now, it's very important that we use the correct wording, and we're talking about various different colours or shades. Notice that with calcium and strontium, they are both red, but calcium tends to be a slightly paler brick red and more orangey, whereas strontium is a crimson red. And you can see that when you compare the calcium to the strontium. Okay, but this also could be lithium, because lithium is also red. So this is where the problem arises when we're having to do flame tests. Now, a typical question in a Unit 2 paper is asking how flame tests actually occur. And this is typically 4 marks. So I would strongly suggest that you memorise this process, because it can be an easy 4 marks to pick up in an exam. So the reason that we get these colours in our flame test is caused by something known as an electron transition between our energy levels. And you should know that the word transition means to change or even to move. And that's what's happening here. We're getting the movement of electrons between different energy levels in our atom. So when the electrons absorb energy from the flame, they're going to absorb it and they are going to move to a higher energy level. And this is sometimes known as excitation or promotion. So they are being excited or promoted to a higher energy level. Now, as with physics, what goes up must come back down. The electron then loses this energy and it falls back down to its ground state. And ground state just simply means the original energy level. And as it falls back down, it is going to release the energy that it absorbed. And this energy that is being released is in the form of light energy or a photon. If this energy is a wavelength that is within the visible region, then we're going to see a characteristic colour appearing. So the wavelength has to be between 400 nanometers and 800 nanometers. That's within the visible region. If we see metals such as magnesium, they appear colourless to our eyes, and this is because they release radiation that is in the UV region. So we don't see a colour for magnesium because it's not within that visible region. The reason that we get different colours is because we have different gaps between the energy levels. And because of that, we're going to see different colours being formed because each of them is going to absorb a different amount of energy to move up. And as it releases that energy, it's going to release varying amounts of wavelength. So we're going to see a different colour for each individual atom. So you can see here that we're getting our absorption of our electron, absorbing the energy, being promoted up to that higher energy level or excited state, and then as it falls back down, it is releasing the photon of energy in terms of the visible region, so we should see a colour, and you can see the colours down at the bottom. Now, you're not going to be asked about what colour corresponds to what wavelength, but you should know that it does need to be within the visible region, and it would form from red, orange, yellow, green, blue, indigo, or violet, or a shade in between there. Now, we also have to know how to test for ammonium ions. This is also a very common cation, but ammonium does not give a colour in a flame test, so we have to identify it using a different chemical test. Okay, and ammonium is NH4. We know that it contains a dative covalent bond, and that's going to give us our positive anion. Our positive cation. We covered this back in topic 3, so if you can't remember the structures, go back and have a look at that in your textbook or back in your notes. So the way that we identify an ammonium cation is we add sodium hydroxide, and when this happens and the mixture is warmed, ammonia is going to react and it is going to form ammonia gas. Please be aware of the distinction between those two. They are not the same thing. Ammonium is the cation, ammonia is the gas. When the ammonia gas is released, we will then test it, and it turns damp red litmus paper a blue colour because it is an alkali or a base. So we see this colour change happening here, and you can see that we've got our ionic equation as well. Alternatively, you can mix the ammonia with hydrogen chloride, and you're going to make the white solid ammonium chloride. This would be an acceptable answer as a chemical test, but typically the most common answer is sodium hydroxide. So let's now have a look at a past paper question. These are all from the January 2019 paper, and we go through various different parts of the Group 1 and Group 2 content. So a flame test can be used to detect a metal ion that is present in a precipitate that can be found in a substance called hard water. So we want to explain how metal ions produce a colour and a flame test. So this is what we were just talking about, and here we've got 3 marks. So the first part is our electrons are excited to a higher energy level. Okay, and this is done by absorbing our energy in terms of a photon or something like that. But what we want to really focus on is we want to have it as being the electrons are excited. Then the electrons fall back to the ground state. And when they do, they are going to release energy. And then the third mark is that the energy released is a photon of visible light. And this visible light corresponds to a specific wavelength. And then that's what gives us our colour. So 3 marks talking about the electrons being excited, then falling back down and releasing that photon of light somewhere in the visible region. So part 2, give the colour of the flame that you would expect to see when calcium is present. Well, for calcium, we see a yellow-red flame, or a brick red flame. Either one of those would be accepted. For part 3, give a reason why magnesium ions do not produce a flame colour. Well, it is because the wavelength of the energy released is out with the visible region. Or you can even say it is in the UV region. Either one of those would be accepted. So for part B, we want to write an equation to show how calcium hydrogen carbonate is formed when dissolved carbon dioxide in rainwater reacts with calcium carbonate. State symbols are not required. So we've got calcium carbonate, which is CaCO3, reacting with CO2, and we said that there was rainwater, so that's our H2O, and we're going to form calcium hydrogen carbonate, and the hydrogen carbonate is a 1-, so that means it's going to be in a 2-to-1 ratio with the calcium. Part C suggests why calcium sulfate and magnesium sulfate can form hard water, but barium sulfate cannot. Well, this is all to do with the solubility of sulfates, and it is worth 1 mark. So we simply say that barium sulfate is much less soluble than calcium sulfate or magnesium sulfate. Okay, you can also say that barium sulfate is insoluble, or you can even refer to the trend and say that the solubility of sulfates is going to decrease down the group. All of these would be accepted for that 1 mark. And then the last question is a thermal stability question. As I said, they are very common. So group 2 metal carbonates decompose on heating as shown in that reaction. Explain why calcium carbonate requires stronger heating than magnesium carbonate. Okay, so now we want to be thinking about size, charge, and polarization. These are the key things that we want to be thinking about. So if I've got calcium carbonate, CaCO3, and magnesium carbonate, MgCO3, both of them are 2 plus. So we know that they're not going to really be affected by the charge. So this time it must be the size. Now, magnesium is above calcium in the periodic table. So that means that calcium ions, or Ca2 plus ions, are larger than magnesium ions. So because we're getting a larger ion, that means we're going to have less polarization. So calcium ions polarize the carbonate less. Okay? Or you could even say they polarize the CO bond less. And because they are polarizing that less, that means that the CO bond is less easily broken. Okay, or you require more energy to break these bonds. Okay, so we're looking at the size, saying that calcium is bigger, therefore it is less polarizing, and the less polarizing it is, the more difficult it is to break those bonds, so it requires much stronger heating. And that is your 3 marks. So there's your mark schemes for everything in the January 2019 paper, if you have been trying these yourself. That's everything for topic 8b, the elements of group 1 and 2. Hopefully everything has made sense, but if there's anything that you are not sure about, please feel free to leave a comment below, or certainly ask your teacher or check with the textbook. And we hope to see you back on the channel very soon.